And good evening. Welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here at Kopernik. It's great to have you here on Black Friday. Anybody get some good deals today? Mostly online, right? Well, it's great to have you here in person, but also want to welcome those watching on our live stream. And I'll talk a little bit more about our live stream in a moment or two. Just by show of hands, who's here for the first time or not since your 4th grade field trip? Okay, very good, very good. Who here are members? Oh, okay, excellent, excellent. Well, the people that raise their hands second have a valuable piece of knowledge, and that's the value of a Kopernik membership. We are a nonprofit organization, and so we have to find ways to raise money, one of which is through memberships. But more specifically, what's great about a Kopernik membership, not only do you get into here on a Friday night, but we belong to what's called the ASTC, Association of Science and Technology Centers. And there's over 380 other science centers, much like ours, but most of them much larger than ours, that honor our membership card. So you could go to Roberson for free. You could go to the Museum of Science and Technology up in Syracuse for free, or Ithaca Science Center, or the Franklin Institute down in Philly, or the Intrepid in New York City. So if you like this kind of place, getting a Kopernik membership is actually a pretty decent deal. You'll find actually, I took my daughter to the Franklin Institute a few years ago, and just had we both paid just an adult and one child, it would have been more than the family membership would be for a whole year. And plus we skipped the whole line of people trying to get in to get their tickets. So if you like this kind of place, consider getting a Kopernik membership. We are actually just celebrating our 50th anniversary here. It was constructed in 1973, but actually opened in 1974. A few months ago, we actually had our 50th anniversary gala down in Binghamton, and now we're actually about ready to announce our Reach for the Stars campaign, where we're going to sort of set our course for the next 50 years. So stay tuned for that. We got some exciting plans coming up. So Kopernik, we do a number of things. We do a lot of school outreach. In fact, on Monday morning, we've got another school group coming up here, and so we always enjoy having them come up. We do a lot of school outreach. We actually take our resources into schools. And summer camps, we have summer camps for students as young as entering 2nd grade through high school. And these are week-long camps that focus on a wide range of STEM topics. But always Friday nights from March to mid-December, we always do these Friday night programs, and I really enjoy these because it's really an opportunity for us to really promote what we believe is really important is lifelong learning. So, especially you students that are here in the room, learning doesn't end in 12th grade or at the end of college. It's something you should be doing your entire life. And I remember, watching. I'm dating myself here, but watching Neil Armstrong on the moon, right? And the computers that they used to, in my phone here, this is more computing power than all of NASA had when they were trying to get astronauts to the moon. And I wonder, okay, what's going to happen over the next 50 years? How will technology change? And it's you young guys, you young people that are the ones that are going to make that happen. So stay in school and think about a STEM career. But anyway, Friday nights we always do these public programs. And back in 2020, when COVID hit, we had to stop. We couldn't gather people in a room anymore, so we figured, look, we'll just stop doing this for a couple of weeks until this COVID thing blows over, and that didn't exactly work out that way for us. So about a month or two later, we said, look, we've got all these speakers lined up. Why don't we have them Zoom into us, and then we'll just turn it right back around and put it out on a YouTube channel. And so if you actually go to YouTube and go to, just type in Kopernik Observatory and Science Center, you'll see our YouTube channel. We have now almost 14,000 subscribers. Every one of our Friday night programs, we live stream. How many people are on the live stream right now? 23 people, about almost outnumbering the people here. So, we often have people literally from around the world. There's a woman, Lindsay, in Adelaide, Australia. Everyone say hi to Lindsay. There we go. She's having breakfast now in Adelaide, Australia, watching our program. So, but what's great about these programs is that you can watch them. If you can't come up here in person, you could watch it on the YouTube channel. But also, this recording will be available after, once we're done here. So you can actually, tomorrow or next week or next month, you could go to our YouTube channel and watch this program. But you could also go to any of our other programs. Last 2 weeks ago, we did one on CRISPR. I did one on astronomy, mythology, and the keeping of time. We had meteorologists from the National Weather Service talking about tornadoes and how there are 32 tornadoes in New York State. So it's not always about astronomy, but it's always something that's interesting. And but today is our data always on Black Friday. We always have our black holes on Black Friday presentation. And this evening, Roy Williams is one of our educators, is here to talk about one of his favorite topics.
Okay.
All right.
Thank
So
you.
we're going to pass it over to you, Roy.
All right. Thanks.
And let's get your PowerPoint up.
Okay. Thank you. Am I on? Yeah. Okay. All right. Thank you. Did anyone really go shopping today? The Black Friday? Is it still a thing? I don't know. I think black holes are going to last longer than Black Friday, so we're going to have to change the name of this program. So yeah, we've been doing this, I don't know, about 15 years or so. So thanks a lot for coming up. You got to see Saturn already, right? So hopefully, if it stays clear, you'll get to see Jupiter. Jupiter's rising right now, so you get to see mighty Jupiter, the big Jupiter. All right, so black holes. Okay, so what are black holes? We're going to explore that. We're also going to learn about stars and life cycle of stars, since that ties in with black holes. All right, so let's see. So this is a classic diagram showing the life cycle of a star. All stars start in what's called a stellar nebula, and they can end up in three basic different endings. Okay, and so an average So anyway, planetary nebula is a term that came from the 1700s when their telescopes weren't quite as good, and astronomers looked out into space and saw these objects. They looked like little planets. So that name kind of stuck. It's not a very good name because it has nothing to do with planets. The second track you see there is more larger stars, more massive stars than our sun, can turn into what's called a red supergiant at the end of its life. And then it explodes. So our sun's not going to really explode. It's more like puff away type of thing. A super violent supernova explosion is what occurs there. And you get a neutron star
or something called a black hole, which we're going to talk about. So you got this continuum of white dwarf, neutron star. The neutron star is it's just as hot as a white dwarf, and it's even more dense. And then a black hole is the most dense object there is. So as you go down the chart here, it's getting higher density. Neutron stars, I mean, to give you an idea of weight, white dwarfs, if you were able to take a spoon and scoop a spoonful out, it'd weigh as much as a battleship. Okay, that's how dense it is, okay? And we're really made of empty space. So atoms, normal atoms, to give you an idea, if you blow up an atom to the size of let's say a marble, the nucleus where it's a marble, you're at home plate, the first electron would be in center field. So we're mainly made out of empty space. So this type of exotic material we've never really seen.
Right,
But-
we just changed your battery.
Oh, no, okay. Were people online?
Yeah, it's
Okay. How many got online right now?
23.
Oh, still 23? Well, they didn't leave for the sound? Okay, here we go.
Okay.
Okay.
That's better. Yeah, we should have noticed that. All right. Sound check. We're good? Okay, sorry, folks. Okay, we got one person in Australia, you said, right? They're far away. They can't do anything. They can't touch me. Sorry for the sound. So we got that fixed. So anyway, yeah. So and then neutron star, you dig it up, and they say, with a spoonful of it would weigh as much as Mount Everest or something. Just to give you an idea. So and black holes are even more dense. Okay. So I think this chart will pop up again, if I'm not mistaken. But anyway, so really the main theme to get out of this is what causes the star to take one of these three routes. Okay. Does anybody see what it is? What's the determining factor that makes it end up? What do you think?
Mass.
Right. It all has to do with mass. So if it starts out small, it's going to end up a white dwarf. If it starts up 5, 10 times bigger than the sun, more massive than the sun, it might end up as a neutron star or a black hole if it's even bigger. So yeah, it's mass. Now, there are some unique situations where a low mass star can gain mass. If it's a binary star going around each other, it can suck material from the other star. That's possible. But by and large, if the star is left alone, it's going to be mass that's going to determine it. Okay. We're doing good? Okay. All right. So what are black holes? They're intense gravitational field left when a giant star collapses. All right. It just collapses during a supernova explosion. And let's see what we got. And the star has to be much larger than the sun, at least 10 times bigger than the mass of our sun in order to get you a black hole. We talked about the star's life cycle, so it's the end of a massive star's life cycle is what a black hole is. Gravity becomes so big that it compresses in forming a black hole, so it compresses everything down and forms a black hole. Now we're going to define what that means in just a little bit. Why do we call it a black hole? Okay, so a guy named Einstein, mathematician, came up with general relativity, and he improved on Newton's theory of gravity. Newton pictured gravity as being a tug between two masses, and to this day that's still fairly accurate, but a more accurate representation of probably what's really going on is the concept of what's called space-time. And so it's the warping of space-time that causes gravity, or mass causes gravity, which causes the warping of space-time. So Einstein describes gravity as a deformation of space-time around a massive object. Neutron star is really pulling down here. We got a little demo here. We'll demonstrate this in just a moment, I think. Yeah, we'll do it right now. So one of the things that proved Einstein's theory was a total solar eclipse in the beginning of the 20th century. I think it was 1917, or either 1917, 1918. But anyway, you got, during a total solar eclipse, you got this unique opportunity to see stars that are nearby the sun, all right? And according to Einstein's theory, the starlight from behind the sun should be visible because the sun is warping space-time. What you see here on this diagram is that you see the concept of the star is really behind the sun. It gets covered up by our moon, or it gets blocked by our moon, allowing us to see the star because the starlight is being bent. It makes it appear it's over here, but really it's behind the sun. So the white path is how it appears to us, but in reality it's hidden behind the sun. And so if Einstein was wrong, you wouldn't see that star. And they did see it. I mean, it was close because the instruments they were using, the photographic techniques they were using, was right on that limit. It's a very small difference. It's not a huge thing. So I'll just kind of demonstrate here with, you ready to go? I'm going to demo this real quick. So we got a little camera here so you get to see it. So we got our, and we're going to do more with this toward the end too. So here's our fabric of the universe. It's also known as spandex universe, okay? And so what we have here is, you can see it's warping. This is the sun. It's warping space-time. And so what we got here is starlight, this marble represented by that. And you're going to see it go by the sun and curve and go that way. So if we're looking over here, the star is here, and Earth is over there, let's say, and the starlight passes there we go. So that's the idea. That's what that image showed you. So I'll go back to that slide now and just kind of show you that. So yeah, I'll come back to that in a little bit, but just do that. Oh, okay, I'll let you do it. Yeah, so that's kind of what I just demoed, okay? So real hard evidence that this is what's really happening, all right? So star formation. Stars, we mentioned stars form in nebula. This is part of the Eagle Nebula. It's one of the first objects the Hubble Space Telescope took pictures of. And this part of if you've seen the classic picture, Pillars of Creation, this is the part of it. This is a zoomed in portion. And you can see these little globules here, and right there. This is where stars are forming in these little eggs, they call them, which stands for something I'm forgetting. But anyway, and that's where they are. So there's a whole bunch of stars forming. And what's going on here is that it's emitting UV light, and it's ultraviolet light, and it's actually glowing. So this nebula is actually glowing because of the UV light. So any questions on this? We're good? Okay. So when is a star a star? A forming star is considered to be a true star when nuclear fusion takes place in its core. So we got these things called protostars. I think we're going to talk about that. We've got four hydrogens fusing together to make helium, and they release a lot of energy. All right. It's actually a complicated process, 3 steps, known as the proton-proton chain, and of course it's you calculate the energy. You've all seen that formula before, and so that's Einstein's famous equation. Energy equals the mass times the speed of light square. So the speed of light is one of these strange constants that we're not really sure why is it that speed. Why is it 3 times 10 to the 8 meters per second, or 186,000 miles per second? Why is it that speed? So that's one of the things we really don't know. But it's tied into all this. So after all his calculations, he comes up with this elegant formula that looks just like that. And so if you get something simple like that, I think that shows you're on your right track. It seems that way. Philosophically, why that's the case, I don't know. But anyway, so energy. So what's going on here is you got missing mass. When hydrogen fuses to make helium, you get this, and if you were to weigh the helium, it would weigh actually a little bit less. So what you get is that mass is turning into energy. So here's the complicated thing. I'm not going to go into that. Okay. So that's the proton-proton chain. So, all right. Just to give you an idea of size, you got this red giant star, and you got the sun, and you got the Earth. Just kind of give you a comparison. You can fit about 110 Earths across the side of the sun, or 10 Jupiters, something like that. So anyway, so contraction of gas. So protostars, before they become stars, they contract due to gravity, okay? And you reach a certain temperature and pressure. Electrons are stripped off of their parent atoms, creating a plasma. Plasma is the fourth state of matter. It's You know, you got solid, liquid, gas, but what plasma is, not to mixed up with what's in your blood or whatever. Plasma is it's an electrified gas. It's a gas that conducts electricity. So anyway, releasing a great deal of energy, and this is when the energy from the fusion really starts happening. So what you do is you got a battle between two different pressures. You got the outward pressure of the nuclear reactions, which are happening in the core and pressing outward, and then you got the pull of gravity. So at some point, you're going to reach a static equilibrium. And so, I thought, okay, that's coming up next. So anyway, there's you get new stars, okay? Variety of sizes and colors. So stars are mostly, you got from blue to red type of thing. Surface temperature is what governs the star color. Okay. Anybody know what stars are going to be what color stars are going to be the hottest? Any idea? What do you think? Blue. Very good. So it's opposite of your bathtub. Blue's the hottest. Okay. Red is the cooler stars. And what we're talking about is surface temperature. So if you heat up with a torch, you heat up some iron. They say it goes from red to blue and maybe white, but that kind of demonstrates that. So the more mass, the brighter and hotter. However, the more mass equals shorter lifetime, and that's kind of opposite what you would think. You think if you have more mass, it's going to take, it's going to convert those elements. It's going to take longer. But what's happening is you also have more pressure, and it's happening at a quicker rate. So the smaller stars are the ones that really last a long time. Big stars only last maybe 10 million years or something like that. So less than 1 billion years, I know that. So anyway, we've been able to see some of these protoplanetary disks using infrared telescope like the Spitzer. We've also, the Hubble Space Telescope, one of its first images, did that as well. I think I have images of that. Let's see. No? Okay. So anyway, so you get this, with a lot of things, you get this stratification of different layers going on. That's the kind of thing we see with objects. So after millions to billions of years, there's no hydrogen, all right? Without the outward pressure from these reactions, the outer layers of the star begin to collapse inward. Newly generated heat counteracts the force of gravity, and the outer layers of the star are now pushed outward. The star expands larger and larger. So this is more like the red giant phase it's describing. As it runs out of fuel, as it runs out of the hydrogen fuel, it starts turning into a red giant. Then it's going to start creating the other elements. So keep in mind that when the Big Bang occurred 13.7 billion years ago, there was really only hydrogen and helium. It's only through this nuclear fusion that we get these other elements, the stuff that we're made out of. As Carl Sagan said, we're made of stardust. And this process will go all the way until it hits iron, which is only number 26 on the periodic table. And it hits iron, and then the thing explodes like a quarter of a second later. So, and then it creates all the other heavier elements, okay? So anyway, if you come up here during a sunny day at Astrofest or some other event that we do during the day, we have special filters to see different layers of the sun. We have a hydrogen alpha filter that allows us to see prominences. We can see through our white light filters, our projection, and our heliostat over here. In physics, you can see sunspots. Okay, so anyway, this is that static equilibrium we talked about there. So it's gravity's trying to pull it in, but the gas pressure is going outward. Okay. And so now we're back to our classic diagram. So so now let's talk about the more denser objects, the larger massive bodies here. Here's some planetary nebulas. Again, this is what's going to happen to our sun. So the core of the star is all that remains after the planetary nebula is shed. And that's what we call a white dwarf. All right. So white dwarf forms if a star has less than 8 solar masses. So that was the number. Okay. So more of them. Okay, so they're quite beautiful. And keep in mind, it depends on the angle we're observing them at. Just like you saw Saturn today, how it looked edge on. So this is more of a top view, looking downward. That's one way of looking at it. This might be more of a side view. Okay, so. All right, so what's going on here? So basically, a black hole is so dense that at some point, this gravity is so strong that not even light can escape it. Once you cross a certain line, light cannot escape the black hole, and that's why they call it a black hole, because it shouldn't be able to really emit any light. And so the only thing we really see is things indirectly observed black holes. All right. So when I was in high school, they were really theoretical. Okay. And people would see these X-ray, astronomers would see these X-ray sources in the sky, and they were theorizing those are the black holes. Okay. And so what goes on here? A lot of stars are binary. 2/3 of the stars out there are binary stars, which means there's more than one star. And so these black holes might be able to suck gas from another star, and it will spiral into the black hole. All right, and as it does that, it's going to energize that gas, turn into a plasma, and then it's going to radiate X-rays. And you can see it creates a magnetic field that shoots out the X-rays along this axis perpendicular to the plane of the spiral of the black hole. So the spiraling material going down into the black hole. So that's a classic artist conception, of course. Oh, geez, you didn't see that. So yeah, go ahead.
Can that star have planets revolving around it as it's going around that black hole?
Yeah, that would be in trouble, right? They would probably be in trouble. I think so, but they might be in trouble if they were far away. You'd want them to be far away. Now, there's something called the Goldilocks zone where you'd want to be. So I bet you that would disrupt a lot of that type of stuff. And you certainly wouldn't want to be in line of the path of the X-rays that are shooting out. So, but anyway, so things get sucked into black holes. So that's my theory. You know, I have a problem with losing things. So I really believe that, where do the socks go? I do believe there's probably a small black hole in your dryer, and so, but matter can't be destroyed. So they got to turn into something else, and I think they turn into these things. Yeah, so you got lots of lids, right? So it's got to be your socks turning into lids. That's the only thing I can. That's my theory. So I don't care what Hawking says about it. Okay, so orbiting a black hole. Yeah, so that's a typical thing. Again, an indirect way of seeing it. If we didn't have that star there, we probably wouldn't see it, or we might see the X. Yeah, we probably wouldn't see it. So it's all about indirect evidence. Accretion disk is what they call that, right? So material from a companion star, and it's sending out X-rays. So X-rays are very energetic. So X-ray sources. Okay. All right. So let's talk about where we are and where's our black hole near us, if there is one. Hopefully there isn't, right? Because that'd be pretty scary, right? So you are located right here. We're all located right here. We're in the Orion arm of the Milky Way galaxy. When you look this way, you're looking towards Sagittarius, the Sagittarius arm. And probably all the stars you see in the sky is probably just about here, I think. You know what I mean? Anyway, you can look that way toward the center of the galaxy and very carefully, see something called our supermassive black hole that we now know exists in the center of the galaxy. So I got a little video we're going to show on that. Let's see, and this is it here. This is to remind me to go to it. So I'm going to go to YouTube now. Are you ready? So, okay. So, because I never get those links to work. Just like I don't find my socks. I don't find the links to work. Okay, so this one, that's your intro. This one would be good. No sound, I'll just talk. So you're seeing 20 years of a time lapse, and you're seeing, let's just look at this stuff going, like what's going on. These are stars in the center of our galaxy. It's going around something called Sagittarius A. So you can kind of see where these stars are doing these crazy speeds and orbiting it. So you can orbit a black hole and not get sucked in. That's definitely possible. Yeah, so 20 years of data here showing this. Now, I think I got a better one that kind of shows the paths a little better, but I just wanted to show you kind of the raw footage. So that one does it, but hold on. I think I got, yeah, this one. Let's see. Yeah, we're going to zoom in, and here we go. So we're zooming into Sagittarius A. And again, we're looking toward the center of our galaxy. Sagittarius in the summertime is kind of low to the south, and you can see that it's kind of dense with the Milky Way, so to speak. So you can kind of see this in the sense that there's more stars there. And as we zoom in and get closer and closer to this area, we're looking toward the center of the galaxy. And here we go. So the goal here, what you can do is that using Newton's laws of his gravitation, you can calculate the mass of the black hole. Because if you have something going around it, and if you know the mass of the star, and you can calculate how fast it's going, and you can figure out the force, and therefore you can figure out the mass of the black hole. So I want to say it's like about 4 million times the mass of the sun. Yeah, 4 million times the mass of the sun. So yeah, here we go. So I wanted to show you some orb. Yeah. So it gives you the date. So this is real evidence that something is really happening. You know, that there's Sagittarius A, they labeled it. Okay. So that just kind of shows you the indirect evidence of what's going on. So, okay. Yep, go ahead.
Star does get sucked into a black hole, it's a really slow process anyway.
Well, it's going to rip apart as it gets closer, and it's going to go down into that accretion disk. It could probably be pretty fast, though. I don't have but it can happen fairly quickly, I think. But yeah, it does happen, absolutely. So let me see. Back to my slideshow. So yeah, we saw that. Okay, so anyway, so we've now been able to use something called the Event Horizon Telescope, and the Event Horizon Telescope has been able to take what the Event Horizon Telescope is. It's called an interferometer. It's telescopes in the United States, the west coast of the U.S., and then in Europe, and they're using, basically making a telescope the size of the Earth almost, and they can develop these pictures of what it looks like. So this is from data. They're not real pictures. It's not like you're using a CCD or a film, but it's a complex process. But anyway, that kind of shows how the accretion disk. So we have been able to take pictures of that, so to speak, using that method. This was the first one they did. This is the one at a much larger black hole, which is in M87, a galaxy M87, and I think this is about 1,000 times bigger than our black hole that's in the center of our galaxy. So let's talk a little more detail, just theoretically black holes. So again, something called the event horizon. This is the line that if you cross, you cannot escape. And we're talking about light. So technically there would be an event horizon for a spaceship too, which would be even further away. So light would be closer. I mean, light is the fastest thing there is, right? So if you can escape, if you're just outside the event horizon, if you're a piece of light, a photon, you can escape. But if you're in a spaceship, you're done. Okay. So there's probably another radius out there where it depends on how big your spaceship is and stuff like that. But anyway, so Chandra, an Indian mathematician, again, another beautiful, elegant formula where 2 times the gravitational constant, that's big G as we call it, which Newton was the first one to use that, and then mass divided by the square of light gives you the radius of how far away from the black hole is this event horizon. And so what they mean by event horizon is that once you get sucked into the black hole, you can't escape and come back to the rest of the universe. Okay, so it's yep. So All right. So again, what we're doing is that we're now curving space and time dramatically, and it's getting sucked in. Okay. So according to Einstein's gravity bends time and space, as we demonstrated. Once you pass the event horizon, there's no going back. You're basically taken out of the universe, so to speak, or at least out of our, where we can get to or whatever. You will get stretched and stretched and stretched. So the idea is that if you're going feet first into it in your spaceship, that your feet are going to get pulled faster because it's closer. So I don't know. This is spedification is what you get turned into spaghetti and then you get crashed or get who knows. So no one's ever gone through it. No one's ever lived to tell the tale. Okay. So black holes myth. If black holes will spit you out on the other side of the universe, yeah, they used to they were looking at, I don't know, in the 60s or maybe even to the 70s, they were looking for white holes. Is this matter coming out somewhere else? Okay. So once you're in, is the present understanding. Okay. So let's just kind of like go through a little thought experiment here. So let's say you're on the surface of an object like a star, and as the mass increases, so does the gravitational pull. So you throw a ball up, and it goes higher, and then it's stronger gravity, so it's not going to go anywhere. So if the gravitational pull is such that light cannot escape, then you got what a black hole. So if you had a flashlight and you're standing on the surface, it's not going to go. It's going to get sucked back into it like that. So that kind of demos that. So yeah, here we go. This is probably better. So that's the idea. So here light can escape at this if you're at this distance from it. Neutron star, okay. It gets bent a little bit. It still makes it. All right. Maybe a bigger neutron star. It kind of starts wrapping around, and then eventually a black hole. Light cannot escape. Now this has a strange thing happening here, where you have time dilation, or the idea of clocks running at different rates based upon your vicinity to a black hole. Okay, so what you got here, you're in two spaceships here, and this guy that's further away from the black hole would, according to Einstein's theory, would be experiencing, maybe 50 seconds, almost a minute, where this guy would experience only 15 seconds. So time is slowing down relative to you. Let me see So what I want to do now is kind of show you how it kind of works. So it's really just going to pull down even further. Now we demonstrated. Yeah, so we demonstrated the sun, right? So let's make it even more massive, all right? And I got more marbles. So, oops, okay, thanks. Okay, so now we're going to need a volunteer. Okay, you ready? Come on. So we need to go underneath, and you're going to pull on that. Go ahead and pull on that. You're going to create a black hole. So there we go. So yeah, you're even pulling time space even more, right? Okay, now go ahead and release it a little slowly though, so it doesn't go flying. Okay, slowly, go ahead, release it. We just want a regular star now. So, and then this is light, or planets, or whatever. Ooh, look how they bunch up there. Isn't that cool? But that, by the way, can also simulate how planets form. So not only can this demonstrate black holes, it can do all types of things. So the idea, here's a star, and then here's a planet going around it in orbit. So this explains the orbit. No, we're going to need you though. Hey, can you see the marbles from down below? Okay, all right. So they're going counterclockwise. For you, which way are they going? Are they going clockwise or counterclockwise? You can't tell. Okay, they don't know how to read a clock. That's what it is. Digital clock, right? Okay. So anyway, so this could be planets, or if you have a bunch of asteroids, or what are called planetesimals when the solar system first formed. A whole bunch of them. Watch how they'll group together, because they're gonna warp space-time in kind of like a snowball effect, where you get a mass just by chance. You get them all. See, they'll group together. See that? So that would be a planet forming. Okay. So anyway, all right. Let's go ahead and create a black hole. There we go. What's your name?
Grayson.
Grayson, go ahead, pull on it and get that black hole going. All right, so we got a nearby binary star that's its layers are getting sucked in, and it's gonna come around, and so every time that stuff is, it's warming up, it's heating up, and it's gonna turn into X-rays. So it's getting sucked into the black hole. So the event horizon might be this rim right here. If you're outside here, so this circle we could pretend is the event horizon. So once you get beyond that, there's no coming back, okay? Okay, one more time, we'll just show it. Here we go. So that's the idea. Nice. That worked really good. Okay, good job, Grayson. All right, come back up. See, you're the only person to escape a black hole. So, what was it like? Okay, okay. So in terms of we talked about relativity, changing time. I kind of went over that quickly, but the concept there is that this was also proven when we went to the moon. We on the flights. I don't know if we did every flight, but I know there was at least one. We carried atomic clocks on there, and accurately synchronized them, and it lost some time. So time went quicker here than for those guys. So their time slowed down by a few nanoseconds. I think it was. It was a tiny amount, but it was enough to kind of prove it. So, okay. So how do I get back? Here we go. So I think that's it. Let me see. There's maybe one or two more slides. Oh, Drew, how's the, you gonna check the weather? See, okay. So hopefully you'll get to see Jupiter. Non-rotating black hole has only a center and a surface, singularity. So we're talking about it collapsing theoretically to 1 point. So zero volume, we're approaching zero volume. So that's why it's so dense. All right. Yeah, we kind of talked about that. I think we covered that. We did that. Center of a black hole is a point of infinite density. Zero volume is called a singularity. So I don't know if that's just a mathematical idea or does that really happen. I don't know. But that's the idea. So now, if you put two black holes together, can you get something called a wormhole and be able to use them to traverse space? Okay. Like if you watch Star Trek Deep Space Nine, right? So they're right near a wormhole, and they're able to travel from one. So who knows? Maybe that's possible. So I just wanted to mention that idea. And also in terms of warp drive, the Star Trek. I know Star Trek's so old now, but they're still making them, some derivative of it. But the idea, of warp drive is, from what I can gather, is that they're warping space. So here's our spaceship here. Oh, you want to get the? Yep. Sorry, this part wasn't planned. I'm just spontaneous. Here we go. Okay. So if you can warp space, see that? I can warp space ahead of the spacecraft, and then it goes, right? So what you're really doing is you're bringing. You can't go faster than the speed of light, but if you can warp space, you can bring point A and point B closer. So you can change, and that's the idea. So it would obviously take a lot of energy, so it might never be possible, but all right, any questions?
If you have any questions, I'm going to bring the mic over so that people on the live stream can hear. Okay, hold on.
That's great.
Here's a question.
Yeah. So before you said when a star or maybe even the formation of a star, you have enough pressure to form all the way from hydrogen and helium all the way to iron.
Right.
Where are the rest of the elements?
Right. So so iron is the most stable, and at that point it can't go any further, and then it quickly explodes. And so during that explosion, that's when the heavier elements are created. That's when they're fused together. Well, no, what's going on is they're smacking into each other on their way out. I think that's what's going on. It's an explosion, and so those elements are being put together at that moment. Yeah. So.
We do have a question from the chat.
Okay.
Retrojet asks,
Okay.
are there wandering black holes, or do they hold their relative position in space?
I don't know. What do you think? Yeah.
Maybe. Like, it's like the idea of rogue planets.
Yeah, maybe.
Right.
I mean, everything's moving, right? So,
I mean,
but
right.
yeah,
I mean, arguably, like our galaxy is really moving through.
Right.
Through
Right.
by definition, it's moving.
right. Everything's relative, so yeah, it's sure. So yeah, I would say there probably is. I mean, everything is moving. It depends on your frame of reference. I mean, that's a tough question though. But we're not in any threat of. There's no black holes near us, so we're not going to hit. But we're also lucky in the sense that, as far as I know, there's no stars that are going to supernova that are nearby. Because when those go off, I don't know what the safe distance is, but Betelgeuse is about to go off, maybe in 1 million years or maybe next year, but it's 500 light years away. So I think we're safe. But that's another hazard too. So okay. That's a tough question. Okay.
Another question? Yep.
So there's a theory that there's supermassive black holes. So you have supermassive black holes
Yeah,
all
okay.
rotating around another. So
Okay.
galaxies are all rotating around another supermassive.
Right.
Is there any reality to that?
So yeah, I mean, they can get bigger and bigger. They can keep gobbling them up. Now, eventually, incidentally, as the universe accelerates, it's accelerating. Space-time is accelerating outward, and it's actually getting faster and faster, which was a surprise that we learned in the 90s. And so what you have is the black holes will be the last things left in the universe. As the universe expands, the black holes will be the last thing left, and they do actually leak. It's called Hawking radiation. It's a quantum mechanics thing. You could do a whole program on that, but I don't want to. Anyway, so they do eventually will evaporate, and they'll evaporate 1 times 10. The universe will come to a will accelerate outward, and those black holes will be the last thing, and they'll evaporate and give off their energy 1 times 10 to the 100th power a year. So that's a googol, by the way. So 1 times 10 to the 100 power is a googol, and that's about when the universe will totally die from heat death, which is an interesting idea. So, all right, it's a long time away. So, any other questions? Okay.
Okay,
Well,
I did take a look outside, and the worst. I mean, I had to still get my eyes to adjust, but
Right.
I was seeing some
Okay.
some lights. So I know some of you saw Saturn already. We can, for those that didn't see it, we can get you to do that. I believe Jupiter should be up as well.
Okay.
And I'm not certain
Great.
if the ISS, actually at this point the ISS, even if it did come by, we probably wouldn't see it because we're far enough away from dusk that even if it did come up, we wouldn't be seeing it because what you're seeing is the sun reflecting off the solar panels on the ISS. But there might be some other satellites that maybe are higher up that. So we'll go ahead and take a look outside. But,
Now, who didn't get to see Saturn? So if you can make sure you guys get in the front of the line, so that we can get to Jupiter as soon as possible, because you never know, it could cloud up. And
Sasha, you left it on Saturn, right?
yeah.
Okay.
Okay.
All right. All right. Well, so thank you, Roy.
Yeah,
Appreciate
you're
you.
welcome. Thanks, everybody. Okay.
So next week is a talk on biofilms. There's actually a biofilms department at Binghamton University that will come up and talk about their research on biofilms. And biofilms are everywhere. So come learn about biofilms. The week after that will be actually a movie called The Star of Bethlehem. And it's talking about what might the wise men have seen in the stars. Basically, there was a gentleman who took some software and just sort of dialed it back, over 2,000 years and said, okay, what might they have seen? And so it's sort of an examination of that. And then finally, to close out the year, on the 22nd of December is Dr. Tom O'Brien, who teaches at Binghamton University, and he's going to talk about this sort of intersection of science and religion and how they do, in fact, and can, in fact, work together, as it were. So anyway, thank you all for coming tonight. One thing else, especially for those of you that are new, I don't know if you notice them, but there are deer out there. And so when you're heading out, watch for the deer, drive slowly. I tend to drive down the middle of the road. It gives me a couple extra milliseconds of reaction time. And it's, Sometimes that helps. But anyway, look forward to seeing you up here, but also seeing you out in the scopes.